Hello, everybody. Welcome back. So let's just jump right into it. This one's going to be a little bit longer, so I'd like to go through it a little more quickly. It's probably going to have to be two videos that I make out of this second part, but I will upload them both and I will let you know. Okay, so um, to we're still talking about gases and how they change with pressure and temperature, volume, and moles. And so to conduct some experiments, a 10-liter flask was equipped with a movable plunger, as illustrated here. It's filled with enough H2 gas to come to a pressure of 20 atmospheres. And so this is commonly called a piston. This is what would be in your car, something that is going to be able to have a movable plunger and change the volume of the gas and the pressure, etc. Okay, so in the first experiment, we're going to decrease the temperature in the flask by 10 degrees Celsius. And then afterwards, we will increase the volume. So when we decrease the temperature, what are we keeping constant? Well, let's see if we go PV equals nRT. It doesn't say anywhere that we decrease the volume. So this is going to be staying constant volume. And so what I'm going to do is I'm going to put them both on the same side. But I'm not going to touch temperature just yet because I want to show, probably won't touch it at all. I just want to show you the relationship between the two values. So this is going to end up being P equals nR, and I'm going to put V over here, and then I'm going to multiply it by T. That way, T, temperature, is going to be outside of these. So we have P equaling nRT, nR over V times T. And I did this on purpose because the number of moles, the R, which is the gas constant, and the volume are all going to stay the same. And so we have this, and I will even write this as C equaling constant. And I will say that P equals C times T. So we can say that they are all going to be constant. And so if the temperature decreases, you can see that the pressure is also going to decrease. You're going to have a decrease of both. This is a constant right here, so that's not going to change at all. So let's say that this was 2 and you took it down to 1, and this ended up being 2. 2 times C equals 2. We'll take T and divide it in half, which means that P is also going to be divided in half. So that means that P and T are directly proportional to one another. Similarly, for the next one, we now have a smaller, now have a differently heated vessel, but we are going to then increase the volume. And so that way we have PV equals nRT again. And so N, R, and T are all going to be constants still. We're not changing the temperature anymore. We did that in the first one, but we're not doing it now. And the number of moles is not changing. And so we are going to keep this as it is. And we can even say that PV equals C, another constant. It doesn't matter what that constant is, it just has to stay the same. And so in order to keep that the same, if we raise the pressure or lower the volume. In this case, we are going to be we're going to be increasing the volume. So we'll increase the volume. This is going to be lowering the pressure. So if you increase the volume, you'll lower the pressure. That means that these are inversely proportional, pressure and volume. And we can see that here. Decreasing the temperature at a constant volume is going to result in an increase in pressure. If we increase the volume at a constant temperature, we're going to get a decrease in pressure. And so if we look at this again and we change something else, if we then heat it followed by a volume decrease, we're going to do the same thing. We have PV equals nRT. And we want to know what is happening to the pressure again, so we'll keep that by itself. The first change that we do is a change in heat. And we already know that if we change the heat, the temperature, we can rearrange the equation to look like this. P equals nR over V times T. And so increasing the temperature is going to increase the pressure. Same with the volume decrease. So now we have PV equals nRT. All of those are going to be constants. So if we are going to decrease the volume, then we will increase the pressure. And that's what we see here. Increasing the temperature at a constant volume results in an increase in pressure. Decreasing the volume is going to result in an increase in pressure as well, as long as one thing is kept constant. Okay, so we're continuing on to a different law now, and this is Avogadro's law. Now, I don't know if Avogadro actually came up with this law or they just use his name because this has the number of moles in it. All of these named equations are put together so that to create the ideal gas law. The ideal gas law came last. This PV equals nRT came last, and it came from the relationship from all of these different laws together. And so what Avogadro's law says that equal volumes of any two gases at the same temperature and pressure are going to contain the same amount of gas, the same number of moles. If we change the number of moles, we will then change the volume, and if everything else is held constant. And so let's see what that looks like. We're going to rearrange this equation. So give this a shot. Ideally, I would like you guys to be able to do this on the fly. Just if you have a word problem, you should be able to tell what's being held constant, what's changing, and then you will take PV equals nRT and arrange it into the problem that you need for that. Okay, so for PV equals nRT, everything except for the number of moles and the volume is held constant. So we have PV equals nRT. We will divide V on both sides, and we will get P equals nRT over V. And oh, my mistake. We have PV equals nRT. We want to keep the number of the volume and the number of moles constant, and so we need to get those on the same side. So we will divide by P on both sides, and we will get V equals nRT over P. And then we will divide by moles, and we will get V over N. So that gives us that. We can cross out the things that are no longer with us, and we have V1 over N1 equals RT divided by P. All of these are constant, which means that we can set that equal to V2 over N2. And then remember, one equals I and two equals F. It doesn't really matter if you use I and F or one and two, just as long as you keep it consistent. And we end up getting this, V1 over N1. You can just cancel that out right there, and we get V2 over N2. And so let's go ahead and try to put this into practice. So this is the practice for that, and we're going to use that V1 over N1 equation equals V2 over N2 right here. Go ahead and try this out and take this hint into account. You can make assumptions here. I'll explain after, but what I mean is that you can make assumptions for the number of for the values that you have. Okay, so here's what I mean. When we're talking about making assumptions, what we're talking about doing is taking this we can't assume 3.6 megameters cubed of gas. This is our volume. We cannot assume here, but we can assume the number of moles. All we know is that the number of moles is doubled. So it doesn't matter really what that number of moles is. Let's go ahead and make this define our variables. So V1, we have 3.6 megamoles or mega meters cubed. V2, we don't know. We're trying to find what the volume is going to be. Now, N1, all we know is that the moles are doubled. So we're going to assume here that we have 1. That way, N2 can be 2 because the moles are going to be doubled on the other side. 1 doubled is 2. And so we have V1 over N1 and V2 over N2. Let's just plug them in. We have 3.6 mega. I'll even make it easier. We will just rearrange this. So, in order to get V2 by itself, we'll have to multiply N2 on both sides, um, N2, and then we get V1 and do a lowercase n 2 divided by N1 equals V2. And so V1 will plug in, and 2 will plug in, and 1 will plug in. That gives us 3.6 megameters cubed. And we'll multiply that by N2, which is 2. Divide that by 1. So all we really have to do is just multiply that by 2. And so that's going to end us up with 7.2. I'll put the units down there because I'm out of space. Megameters cubed. 7.2 megameters cubed. All right, that's all you got to do for that one. Okay, so this is a term. We're going to move on to the next thing. So this is a term that we use to define um, a standard temperature and pressure. So STP is what is going to be used a lot, and this is always going to be the exact same thing. So exactly 0 degrees Celsius, which, if you'll remember, is 273.15 Kelvin, right? Because all you do is add 273.15. Exactly 1 atmosphere of pressure, which could also be written as 101 kPa, could also be written as 760 millimeters of mercury. So all STP is saying standard temperature and pressure. We've chosen this to be our standard temperature and pressure. And it was also found that um at STP, you will have 22.4 liters of gas for every 1 mole of gas you have. This will always be true. You will have 22.4 liters of gas for every 1 mole of gas. This is just a picture of what that looks like. Within this 22.4 liters is going to be 1 mole of gas. Um, and so if we were to give this a shot, we would say that at STP, how much volume does 1.6 moles of the World War chemical uh weapon sarin gas? How much does it take off? Well, this is a gas. It doesn't matter what kind of gas you have. So let's do this. So if you have 1.6 moles, I'm going to abbreviate this SG. If you have 1.6 moles of SG, put an L there. And we say that for every 1 mole of gas, there are 22.4 liters of gas. All you're doing is multiplying 1.6 times 22.4 times 22.4. We end up with 35.84 liters, which is then going to be 35.8 liters with sig figs. Now, if you had the same amount of N2 gas, would you have more, would it take up more space? Would it have a higher volume or a lower volume? Well, the answer is that this is true for any gas. Any gas. Any gas is going to have 22.4 liters for every 1 mole. So you are going to get the um, same conversion for N2, which means that we will have 35.8 liters um, of N2. It's going to be the exact same. All right. Okay, so if we want to prove the following statement that the pressure of a given amount of gas at a fixed volume is going to be uh is sorry, if the pressure of a given amount of gas at a fixed volume is proportional to the absolute temperature, then we are going to define Edmonton's law. So let's just break this down for a second. If we're talking about the pressure of a given amount, let's define what our variables are. Pressure for the given amount of gas at a fixed volume is proportional to the absolute temperature. Um, so that means that we have a pressure of a given amount. So this means that a given amount is constant. If we have a fixed volume, that is also constant. A given amount of gas and a fixed volume. So it's always going to be the same moles of gas. It's always going to be the same volume. That means that the pressure and the temperature are proportional. And so this is how we'd work it out. PV equals nRT. And so the volume is constant, and so is the number of moles. Those are both constant. And so we'll put them all on the same side, and we're going to do exactly what I did before. So we'll divide volume on both sides, and we will say that P equals nR over V times T. And I'm going to separate that so we can see what the constants are. These are all going to be constant, and you end up with P equals C, we'll put it in brackets, times T, which means that as temperature goes up, the pressure will also go up. As temperature goes down, the pressure also goes down. Same thing. And we can see that as it's written here. So this is exactly what was done. We divided by volume right there on both sides and isolated all of the constants and found that pressure was directly proportional to temperature. Okay, so let's give this is going to be a problem in which you will have to employ this. So let's go ahead and try this out. I will let you uh work this out on your own for a second, and then we will come back. Okay, so you have a 50-liter cylinder at 21 degrees Celsius, and the pressure is 15 atmospheres. Great. So when you see atmospheres, you should be thinking about your R. If you have liters, most of the volumes that are going to be given are going to be in liters. Some of them are going to be in different amounts, but you should convert to liters because the R values are going to all be in liters. And so that is important for the most part. When you see temperature, the first thing you should do is convert that if it is in Celsius to Kelvin. And we want to know the number of grams of O2 in a 50-liter cylinder at 21 degrees when the O2 pressure is 15 atmospheres. And so for atmospheres, we're going to have to look for a specific R value to use. And luckily, I have already got this up, but this is the Wikipedia page for the R gas constant. I just want you to look at the sheer number of gas constants that there are. There are many, many different ways to calculate this gas constant. We will be using mostly just these top three. And we will also be using, where is it? This one. the liters, atmosphere, mole, Kelvin that is in the center of the screen, right there. Because that one uses atmospheres, Kelvin, mole, all of the things that we are used to using. These ones, we might possibly use that last one, the kilograms meters squared, or the kilopascals one. Another one is going to be, or the pascals and the kilopascals one. And so we're going to use the 0.0821. And this is going to be a number that you probably just want to memorize. That is in liters times atmospheres per mole times Kelvin. And these units are all going to cancel out. But let's see what we are doing here. So we have um, n, we want to solve for n, because if we solve for n, then we can solve for the number of grams that we have. So if we solve for n, that's how we can get the number of grams, because we can use the molar mass, grams per mole, which is excellent. So whenever you can use grams per mole, that's just a perfect thing. It's easy, it's easily calculable, it's on the periodic table, so that's great. So what we'll do is we'll take the pressure, which is going to be 15.7 atm, and we'll multiply it by the volume. We've rearranged it already over here. That's very kind. It's already been done for us. The volume, which is 50.0 liters. Now keep in mind that we have the same units up here already, so that's perfect. Then for the R, we're going to use that value, 0.0821. That is the value that we'll use for this, because the units are going to cancel out, and we'll multiply it by the temperature. So we get the temperature, which is going to be 294 degrees, or 294 Kelvin. So just to show you exactly how this works, it'll work out every single time that you do it. And so we'll say that we want to try to find n. Let's start by canceling out Kelvin. So Kelvin is going to cancel out. Wonderful, which leaves moles by itself. Atmosphere is on the top. Atmospheres are on the top of the equation, so atmospheres can cancel out here. Liters are on the top as well, so liters will cancel out here. The only thing left is moles, but it's 1 over moles. Right? So if we canceled everything else out, if we have liters times atmospheres divided by moles times Kelvin, and we cancel all of these out, we're left with just 1 divided by moles. To get that 1 away, we can say 1 divided by 1 divided by moles. This is going to give us moles. And this is exactly the units that we're looking for right there. So all we have to do is multiply those values together, and we should be able to get our answer. And so what we'll do, what this is going to end up with is 32.1 moles. Now, we're not done, because this is moles of O2. The next thing that we need to do is, I'm going to do it up here because I'm out of space, but we have 32.1 moles of O2. Um, we need to now use the grams per mole to find the number of grams, because that's what the question is asking, the number of grams. So we have 15.99 grams per mole. And so what we will do is we'll put moles on the bottom. So we'll put 1 mole on the bottom, and 15.99 times 2 is 31.98 grams on top. Multiply across, that gives us a wonderful little value of ooh, 1,026.585 grams. However, with significant figures, we're left right there. So we have to put this into scientific notation. 1.026, nope, 1.03 times 10 to the third grams. And that is our answer. And let's see it again. So we put 15.7, which was the atmospheres here, right there. We had a 50-liter container, so we put that there. We used um the R value that had liters times atmospheres per Kelvin mole. We're left with just 1 over moles, which we will divide by 1. When it's on the bottom, you are going to divide by that. So 1 divided by 1 divided by moles is going to give you moles. And we'll multiply it by 298 to get 32.5, which is about what I got, I believe. 32.1, 32.5. If you're off by a little bit like that, I don't really care. We then are going to take 32.5, convert that to grams, and we're left with 1.04 times 10 to the third grams, which is exactly, well, very, very close to what I got. 1.03 times 10 to the third grams. That's fine though. The reason that you sometimes get slightly off numbers is just because of rounding issues or whatever numbers that you started with. And so I don't really mind if your numbers are a few off. That's totally fine with me. Okay, so gas density and molecular weight determination. So the density of a substance is its mass divided by its volume, right? So that's like grams per milliliter. For gases in specific, we usually use grams per liter because gases are so diffuse. So that means the density is influenced by the temperature and the pressure because we have volume present. The volume is going to be affected by the temperature and the pressure, which means that the density is also going to be affected by that. And we can use the ideal gas law to calculate the density of this gas at any temperature and pressure. So if we have a sample of a gaseous substance at 25 degrees Celsius, we have 0.862 atmospheres and a density of 2.26. We are able to find out the molecular weight of the substance. And so let's go ahead and try that out. So first things first, what you want to do is you want to make one of those little lists of everything that you need. So we'll start with the density. It's going to be 22.26. Oh, my mistake. Go ahead and pause it here if you would like to give it a shot on your own. Okay, so 2.26, our density is 2.26, 26. That is going to be in grams per liter. Our pressure is going to be 0.862. And so this means that our R value, we can put that there, is going to be 0.0821. And so we'll keep that there. And the reason we know this is because this is an ATM, and the units for the R value that is 0.0821 is going to be 8. Nope, it's going to be ATM times liter per mole times Kelvin. Now our temperature is going to be 25 degrees Celsius, which means this is another number that you should probably just memorize. It's going to come up quite a bit because room temperature is the temperature that you do everything at. Room temperature is about 77 degrees Fahrenheit, and 25 degrees Celsius is 298.15 degrees. Oh, it's not degrees, it's just Kelvin. And so we want to keep it in Kelvin. And we can get rid of this because our initial value is just 25 degrees. By sig fig rules, we have to get rid of those decimals at the end. And so we have our pressure, our R, our T. Do we know what our N is? No, we don't know what our N is. We don't know what our N is yet. But that's okay because that's what we're trying to find out. If we're doing PV equals nRT, then we have P, V, R, and T. Oh, so I haven't described what V is yet. So what are we going to do for V? Well, if we look at the units here, this says that we have 2.26 grams for every 1 liter. So we can assume that we have 1 liter. That way we know we have 2.26 grams. We will have our mass of 2.26 grams. And so we'll figure that out in just a second, what our molar mass is, but all we need to do is solve for moles. So we'll plug these values in, we'll rearrange, we'll divide by RT, and we will get PV over RT equals N. And we'll plug in values for that. So our pressure is going to be 0.862. Our volume is going to be 1 liter. We'll divide that by our temperature times our R, so 0.0821 times our temperature, which is 298. And the value that we get out here is going to be 0.03523 moles of gas. And so we'll start with 0.0253523 moles of gas so that we can we're going to start with this number of significant figures just because we'll have to trim it down later, but the more precise you are, the better of a number you're going to get in the end. So we have the number of moles now. And remember that molecular weight is measured in grams per mole. So the next step is going to take the grams and divide it by the moles. So that's going to be 2.26 grams divided by 0.0352 moles. And what we get out of this is 64.2 grams per mole. And so let's take a look. Oh, okay. Well, that is the answer right there. I guess I took out the slide that had the answer in it. But let's give another shot to this. So this is another one. Go ahead and try this on your own. Um, and I will get back to you. Okay. So at 24 degrees Celsius, the common anesthetic desflurane is how you pronounce that. Desflurane. Um, is going to the common anesthetic desflurane is going to be 168.03 grams per mole at a pressure of 804 torr. Now, what is the density of desflurane in grams per mole? And so the first thing that we want to do, it's going to be something very similar, but let's go and make a list of everything that we have. So P, our pressure is 804 torr. We have a molar mass, so our grams per mole for this is going to be 168.03. We'll keep that in our pocket for later. We have a temperature of 24 degrees Celsius, which 24 degrees is 1 degree below 25 degrees, which is room temperature. So 298 Kelvin is room temperature, so 297 is going to be the value of Kelvin that we are going to use. We have um, our volume. Again, we are going to be using the density, so we can assume we have 1 liter. So that is going to be 1 liter. And our R. So what are we going to use for R? So there's a couple ways you can approach this. One way is this is torr. Now remember that 1 torr equals 1 millimeter of mercury. And so this is also equal to 804 millimeters of mercury. So what we could do is we could go to this long list and we could spend time looking at it and trying to find the millimeters of mercury one, which is right here. The torr one is 554.984. That's fine. We can also just take our value and convert it from torr to what we're looking for, which could be the one that maybe we have memorized easiest. So what if we do 0.0821? 0.0821, that's liters times atmospheres per mole Kelvin. And since we have liters and atmospheres, we're going to convert this to atmospheres. So to do that, we have 804 torr or millimeters of mercury. We'll divide that. 804, we divide by 760 um, millimeters of mercury for every 1 atm. Put that over here. And our ATM is going to be, let's see, what do we have? It's going to be a little bit over 1, right? We have, it's going to be 1.06 uh, ATM. Okay, so we can just convert this to 1.06. And so we're looking for the density right here. And we have the number of liters. We assumed it was 1. And so all we need to do is find the number of grams. And we have a way to find the number of grams if we have the moles. So that's what we're going to be looking for, is the number of moles. The moles are going to be what we find. So that's going to be PV equals nRT. We will divide by RT, divide by RT, and we will get PV divided by RT equals N. PV divided by RT equals N. We'll plug and chug. So P is going to be our pressure that we just calculated in atmospheres, 1.06 times V, our volume, which is 1 liter. We'll divide that by um, our R, which is 0.0821. We'll divide that or multiply that by our T, which we calculated to be 297. And once we do this, we are going to end up with a value that is going to be 0.0435 moles. Now, we know from this that to get to grams, for every 1 mole, we have 168.03. So we'll take that. 1 mole equals 168.43. That gives us 7.304 grams. And so that's the number of grams. We're dividing it again by 1 liter, right? That's what we decided the volume was. So that's going to be 7.30 grams per liter. I'll put this here so we can keep track of it. 7.30 grams per liter. Okay, so another problem of this. Let's see. We have three 3.0 liter flasks, each at a pressure of 878 millimeters of mercury. And they're in a room. The flask contains helium, argon, and xenon, respectively. We want to assume that the flasks are closed. So, which of the flasks is going to contain the most atoms of gas? Well, we know from 22 from the 22.4 liters per mole that this is going to always be the same amount. Each one has the exact same pressure, so we will say that there is going to be the exact same amount of moles. And so all flasks are going to contain the same number of atoms if they all have the exact same pressure and they are exactly the same volume. Um, which of the flasks has the greatest density of gas? Well, let's see. The highest molar mass is actually going to have the greatest density of the gas. And so we'll get into exactly why this is in just a little bit. But if you have a higher molar mass, then you have a higher density of your gas. And if you heat the helium flask and the argon and you cool the argon flask, which of the three flasks would be at the highest pressure? Um, let's take a second to think about this one because this one's a little bit tricky. We have helium, which is going to be um, which is going to be it started at 878. We heated that. Argon, which was at 878, we cooled it, and then the xenon, which is going to be at 878 continuously. And they're all going to be the same. So all this is what we mean by when we're talking about an ideal gas. Ideal gases have all of the same properties. If we have the only difference is going to be the density. When we have the density, that's going to change the amount of mass. Because if we think about it, we have if we have the same number of moles of gas in helium, argon, and xenon. We have the same number of atoms, which means we have the same moles. We take a look at the periodic table. We have helium at 4, 4.0. I'm just gonna put 4. We have helium at 4, we have argon at 40, and we have xenon at 131. These are in grams per mole, which means that if we have the same number of moles, then we have 1 mole each. We'll have 4 grams, we'll have 40 grams, and we'll have 131 grams for this second one right here. And if we have the same volumes, that means that's 4 divided by 3, 40 divided by 3, and 131 divided by 3. That means that xenon is going to have the highest one because that's going to be 131 divided by 3. Okay, but onto this one, the only thing that changed here was that we heated up the flask with helium in it. Now, the mass of helium does not change the amount of pressure in there. It's just the amount of helium that you have or the temperature that it is. And um, so the highest pressure is going to be the one with the highest temperature. And if we took the temperature of the helium one and lowered it while we raised the temperature of xenon, which of the three flats would have the greatest number of moles of gas? Go ahead and think about this one for a second. I'll give you a hint. There is something already written on here on this slide that is going to tell you the answer to that question. Okay, and so the number of atoms is unchanged. If you have the same pressure and the same volume, then you're not going to have a different sorry, if you have the same moles of gas to start with and they're closed, then you're not going to have a different number of moles of gas. The number of atoms is not going to change, which means the number of moles is not going to change, etc. Okay, so we're going to revisit stoichiometry here. Stoichiometry, the ratio of one thing to another. This is how we are going to be able to do some pretty complex problems. Okay, so this is an example of it. We're going to just use all of the things that we have already done. We use all of the tools that we've already learned in here, and we are going to try to find the value that's given here. So this is a true fact. And in airbags, in airbags are inflated instantaneously by with nitrogen gas by using this compound called sodium azide. Sodium azide is a poison, but it is also used as a way to inflate gas really quickly because it releases a lot of um, nitrogen gas all at once. And so, how many grams of sodium azide would be required to provide 75 liters of nitrogen gas at 25 degrees Celsius and 748 millimeters of mercury? All right, give it a shot, and then I will help you out. This one's a little bit more complicated. Okay, keep in mind that this equation is not balanced. So the first thing that you want to do, here's what I'll do. I'll write out a list of the things that you should do. So first, you want to write and balance an equation. And this is going to come up later as well. I have a much harder version of this that I would like to show you guys. So first, write and balance an equation. That is step one. Then you're going to make a known and unknown list. So that's what we've been doing so far. Make a known and unknown list. Then you want to find any of the molar mass that are needed. So you will know if you will need a molar mass because you will get something that says grams in it. If you see something that says mass or grams, think molar mass. That should be the first thing that you think if you see mass or grams. So find molar masses. All right. Then, for four, what you're going to want to do is you're going to want to convert to usable units. So, for example, we have 748 millimeters of mercury. We can use the R value that has millimeters of mercury in it, but that can get confusing, and it's not something that we might have memorized, right? You really only need to memorize one, and then the conversions that will go to be able to solve for that later. So, if you have millimeters of mercury, maybe we want to convert that to atmospheres because we know that that's going to our R value for that is going to be 0.0821. Convert to usable units. Then after that, you're going to rearrange the ideal gas law, PV equals nRT, to solve what you're looking for. And so we know that we are looking for the number of grams of sodium azide that we're going to be using. And then we will do a little bit of plugging and a chugging. And so we're going to do a plug and chug. What that means is basically you're going to take all of the values that you have and plug them in. So once you have gathered everything that you need, you can just plug things in. So plug and chug. And then your final step is going to be to convert. So anything that is left, you don't want to forget sig figs units. Don't forget your sig figs and units, but whatever you're ending up in, you're going to need to use that. And so I know that we're going to need to we're going to have to convert at the end because we are in grams right now. And if we're using PV equals nRT, then that means that we're going to end up with um we're going to end up with moles right there, right? We'll have all the other information except for moles, which means we're going to have to use molar mass at the very end. And that is going to be one of the things that we already did. So let's work through this. For step one, we want to write and balance the equation. Now, let's go ahead and do that. I'm going to take this and I'm going to shrink it a bit. And actually, now would be a good time to stop as well. So if you weren't sure how to start, and so you just continued the video, this would be a good place to continue from now that you have more instructions. So I'll pause right here. Go ahead and try it yourself. Okay, so we have sodium. We have one sodium on the left, two on the right. So I'll put a two right here for now. And we might have to change it, but that changes the number of nitrogens I have to 6, so I'll put a 3 right here. and that is that. Now, the iron, we'll move on to the iron. Iron is at 2 on the left and 1 on the right, so I'll put a multiplier of 2 right there. That's perfect. And so now, though, we have 3 oxygens and 1 oxygen on the right. So I'll put a 3 right here. Now that changes the number of sodiums I have. And so I will have to change that to 6 sodiums over there, which changes the number I have right here. 6 times 3 is 18. And so we will have to put a 9 on the right-hand side, and we will double check. We have 6 sodiums, 6 sodiums. We have 9 nitrogens, 9 nitrogens. Or sorry, 18 nitrogens, 18 nitrogens, 2 irons, and we have 3 oxygens. So now it is balanced. The next thing I want to do is I want to make a list of all the things that I have and all the things I don't have, all my knowns and unknowns. So if we're talking PV equals nRT, PV equals nRT. My P, do I know that? Yes, I do. That's 748. I'm gonna put Tor here because it's just quicker. It's fewer letters. V, our volume. We do know our volume. It is 75.0 liters, which is excellent because we know already that we are in liters, which means that we do not have to convert to liters. Our N is what we are looking for. N equals question mark. Our R, well, since we're in liters and we don't have, I don't have the value for Tor memorized for R, so the value of R that uses Tor memorized, so I'm going to say that we're going to use 0.0821, and that is going to be in liters atmospheres per mole Kelvin. And so that's something that we can then multiply, or that's something that we will have to convert. So I'm going to put this and say ATM. Now, the T we do have as well. It is 25 degrees Celsius, and I do have this value memorized. We need this in Kelvin because the units are in Kelvin down here. And so that's going to be 298. Okay, so the next step is going to be finding molar masses. So what is the molar mass that we need to find? So we're looking for the number of we are going to know how many moles of nitrogen gas we have made, but we want to know how many grams of sodium azide we have. So the only time we're going to have to uh the only time we're going to have to convert is when we're going from moles of sodium azide to grams. And we know that because we have the molar ratio of nitrogen and sodium azide present, but we don't have the number of grams. And so we need the molar mass of sodium azide. And so what we'll do is we'll say that NaN3 is equal to 22.99 plus 14.01 times 3, which gives us 65.02 grams per mole. Okay, we'll use that later. We don't need it quite yet, but that's step 3. Now, the next step is to convert to usable units. So far, the only thing that's not in usable units right now is our torr. So we'll do that over here. 748 torr, or millimeters of mercury, same thing. 760 torr divide in 1 atmosphere. And what we get out of that is going to be 0.984 atmospheres. So I'll put 0.984 atmospheres there. Okay, I'm going to erase this so I have a little bit more space, but we now have it in atmospheres. We've converted all of our units to usable ones, and then we need to rearrange PV equals nRT. And so we're trying to solve for N, the number of moles of nitrogen. So N is the number of moles of nitrogen. We will divide by RT on both sides. Just do that. And we end up getting PV over RT equals N. Excellent. Now we plug and chug. So I'm going to make this small as well so I have more space to work with right here. All of those are going to go tiny. I apologize if it's difficult to see. I will upload this in high definition so it's easier, but now we just need to plug these in. Okay, so we will take the pressure, which is 0.984, multiply that by the volume, 75.0, divide all that by the R value, 0.0821, and multiply that by the temperature, which we determined was 298. And all of this will come together. And when we multiply all of that out, we are able to get 3.02 moles of N2. So with 3.02 moles of N2, we are then able to convert that into grams. And so what we'll do for that is we're going to use the equation above, and that's what's going to get us the rest of the way where we need to go. So that's going to be 3.02 moles of N2. We will divide that by we're going to use the molar ratio. So for N2, there's a 9. For NaN3, there's a 6. So that's 9 N2 to every 6 NaN3. And that gives us, we will then use the molar mass, which we took earlier of 65.02 gram. Nope, that's going to go on top. 1 mole of that is going to be 65.02 grams. And that will give us a final value of our actual, of the grams that we need, which is going to be 131 grams of N2. Okay. And so if you'd like a different breakdown, this is exactly what we do. We take the balanced equation, we'll convert the pressure to atmospheres, we'll convert the temperature to Kelvin, and we'll find the number of moles. Number of moles is going to be, we'll rearrange the ideal gas law to find the number of moles, and we will end up with 131 grams NaN3. Going into gas mixtures, we have this man Dalton who was able to find that when gases are all together in a single container, they pretty much behave as if they are just one gas. They don't really react much because there's so much space in between them. When you have a container that's pretty large, and you have all of these different individual atoms, they just don't have enough time to really make contact. Very rarely they will make contact, but it is, again, very rare, especially if they are not charged or anything like that. If they are uncharged, they'll probably just stay away from each other. And so, the way that he was able to find this out was in relations to pressure. So, in this image on the left, we have a flask with helium in it at 152 millimeters of mercury. And in flask B, we have O2 molecules at 608. And when you fill flask A with oil, forcing the helium into the flask, the new pressure is going to be the additive pressures of both of those things. So you have 152 plus 608. That is going to be the entire pressure found in the right-hand flask. So really what this is saying is that they just behave ideally. They behave the way that they should. So, because of that, you can say that partial pressures are going to be the sum of all the different parts of the pressures. So, in this previous experiment, there was helium and H2. So, helium and H2 where helium would be 152 and H2 would be 608, to give a total of 760 for the pressure. There won't always be a P3 and there won't always be more. Sometimes it's just those two gases. And so from this, we can also get mole fractions. And so this is a lot like a mass fraction, in that a mole fraction occurs when you are going to divide the part by the whole. So part divided by whole is what's going to give you the mole fraction of something. And so to demonstrate that, let's take a look at this problem. So if we're talking about this one right here, we have a 1 liter sample of dry air at 25 degrees and 786 millimeters of mercury. It contains 0.925 grams of N2 plus some other gases. And so we want to determine the partial pressure. And so remember, these are going to be the things that you use. You'll use P total equals P1 plus P2 plus P3, etc. And you will also use PV equals nRT. And give it a shot. I will do it as well. Okay, so to determine the partial pressure of the, in millimeters of mercury of the gas, what we need to do first is, well, what we're going to do is we're going to write out all of the different variables we have. So we have a 1 liter sample. That's going to be our volume. So that's going to be 1.00 liters. We have a pressure, a total pressure of 786. However, this is not going to be the pressure that we use. We are going to address that in just a second. That's millimeters of mercury. And then we also have 0.925 grams of N2 and 25 degrees. So this is our mass that we're going to use, and 25 degrees is going to be a temperature of 298. So what we want to do first is we need to find the pressure that's just due from nitrogen. And so that'll probably be something like this. It doesn't matter really what the other ones are. But what we can do first is we can see how many moles of nitrogen we have. And so what we'll do is we will say 0.925 grams. We will divide that by the molar mass of nitrogen, which is of N2 specifically, which is 28. 0.02 grams in 1 mole. That's going to give us 0.003301 moles of N2. Now we'll rearrange PV equals nRT so we can solve for the pressure due just to nitrogen. So PV equals nRT, we'll isolate P and we get nRT divided by V equals P, and then we'll just plug things in. And so N we just calculated to be 0.003301. We'll multiply that by R. Now we are going to get our value in atmospheres when I use this value, 0.0821. So that's a good sign that we're going to need to do some extra work. We're going to need to convert that value to millimeters of mercury so that we can use this value and subtract it. 0.0821, and then we have 298, and we'll divide it by 1. So we end up with 0.8076 ATM. And so we can then take 0.8076 ATM for every 1 ATM. There are 760 millimeters of mercury, and we get out the other end 613.79. Now, our next step is going to be millimeters of mercury. This is just due to N2. So that's going to be our partial pressure. That's our pressure, our P N2. Now, if we wanted to find what the mole fraction in mole percent was, all we need to do is divide this number by the whole. So that would be 613 divided by the whole. 614 is what I will say. 614 divided by 786. We end up getting a mole fraction of 0.781, and which is 78.1% nitrogen. And we can see that again right here. So the first thing that we did was we converted to moles of N2. And then we did the substituting of the gas law with a partial pressure. We rearranged the gas law to get a partial pressure. And then we solved to find out what the partial pressure of just nitrogen was. After that, we took the partial pressure of nitrogen and divided it by the total pressure to get 78.0 or 78.1, depending on if you use extra sig figs. Okay. And so we can answer these questions next. So go ahead and take a second, take a look, and then I'll go through it. So a flask equipped with a valve contains 3.0 moles of H2 gas, and you introduce 3 moles of argon gas into the flask via the valve with this, then seal it. So what happens to the pressure of just the H2 gas in the flask after you introduce the argon? What would it change by? So you've taken 3 moles and 3 moles, and those are going to be directly proportional, right? We have PV equals nRT, which means if you double this, you will double that if you keep everything else the same. And so nothing is going to happen to the pressure of H2, but the total pressure of the gas is going to increase to be double. The pressures are still going to be equal with respect to each of the gases. Each one of those is still going to have its own gas because they are acting as ideal gases. They're not reacting at all. They're just existing. Okay, now this one is a very tricky problem, and if you can get this problem, if you can get the answer to it, or then you can probably do any of the problems that have to do with this. So go ahead and give it a shot. This is one of my favorite scenes in Breaking Bad when Walter White throws what seems to be about 2.06 grams of mercury fulminate onto the ground. It makes an explosion. Now, I want to know how many liters of gas are formed in the instant right after the reaction. So he throws it on the ground, and then there is an explosion that comes out of it. And so, like, in this little bubble, just right after it, the pressure is going to be 310 310 kilopascals is our pressure. The temperature is 106 equals 106 degrees Celsius. And the mass of the chunk is 2.06 grams of HgCnO2. Okay, that's all the information that you need. The rest of it you're going to be able to get from the periodic table. I want to know what the partial pressure is from the CO2. So the overall liters of gas that are formed, the partial pressure of CO2, and then the mole percent of N2.